Okay, so today my talk will be what I call an AlphaFold for material science. Okay, so this work is primarily done by Dr. Chi Chen, who is now scientist at Microsoft Research. Okay, we are also working on it further, and some of the work that you see today will be done by my postdocs, Ziwai Ko, my grad student Tiqi, a high school student Elliot Liu, and my grad student Jesslyn Kua. Okay, all right. Without further ado, I'm going to proceed with my presentation, and feel free to type questions into the Q&A, and at the end of my presentation, I'm happy to take any questions that you may have. Okay. Now, since you are at this this webinar, I'm pretty sure that a lot of you are familiar with computational material science. Okay, and of course, machines and computations have been used in material science for quite some time now, right? So even in 1929, Paul Dirac actually said that the underlying physical laws that underlie a lot of the mathematical theory for a large part of physics and the whole of chemistry are actually completely known. And the only difficulty is basically applying them to solve, to actually make predictions, right? Now, of course, the underlying physical law that he was talking about is the Schrödinger equation, okay? So, and that equation basically governs the properties of all materials, right? Now, today we can already do computations fairly easily, right? Using various material software, including those that are made by MaterialsSquare. So you basically take this Schrödinger equation, you usually use some approximation, for example, density functional theory, you plug it into a computer, and after applying maybe some phenomenological laws like thermodynamics or kinetics or mechanical equations, what you come out with are material properties, right? So things like energies, forces, electronic structure, mechanical properties. Now, today we are not only just able to do such calculations on a single material, but rather we are able to do such calculations in high throughput. So in other words, we can actually run simulations across tens of thousands or even hundreds of thousands of materials, right? And this has led to the development of very large databases of material properties. And just one of those examples is the Materials Project, and I'm of course one of the founding developers of this database. Okay, so today in the Materials Project database, you have about 140,000 crystal structures, and most of them, all of them will have energies calculated, and you have almost more than half of them, you have things like band structures and various other properties. Okay. Now, it turns out that just relying on your first principle calculations is actually not enough, right? So I'd like to show this chart, which shows you the data history of the Materials Project, right? So if you look at the x-axis, this is basically the year, and the Materials Project was started in about 2012 or so. And throughout the years, we have gradually increased the number of materials that is in the Materials Project database. Okay, so starting from around a few thousand structures, we gradually build up to about close to the 140,000 materials that we have in the database today, right? Now, what you will notice immediately when you look at this chart is that the number of materials in the Materials Project database have kind of stagnated, right? So over the past few years, we have stopped at that 100,000 structures or so. We have not significantly increased it, unlike the early years where we actually have orders of magnitude increase in the number of materials, right? And this is actually quite limiting in terms of materials design, right? As we all know, materials design is combinatorial, right? So even if you think of something, a simple crystal structure like the perovskite, and you just assume that you can substitute different A and B species, just given 10 different possible A and B species, and 10 A species and 10 B species, just doing a naive estimate, you get about 10 to the power 7 crystal structures, right? And that is orders of magnitude higher than the number of materials that is in the materials project today. And quite simply, you just cannot use first principle calculations to compute your way out of this combinatorial problem, right? Now, the other problem that you see is that other than the energies, you have other properties where your number of properties are actually much smaller, right? So we still have a good number of things like band structures, but if you look at things like the phonons or the elastic tensors, they are also several orders of magnitude smaller than the total number of energies that we have. And the reason for this is very simple, right? Calculating things like elastic tensors and phonons are much more expensive than just relaxing a crystal structure and getting the energy, okay? Now, unfortunately, the good news though is that we have a way out of this conundrum, right? So even though we don't have the ability to compute everything, we do have the ability, we do have enough data today to start applying machine learning techniques and trying to use the data we already have to learn relationships and predict the properties that are for every other crystal structure that are potentially out there, okay? So, and that's basically the general concept, right? All right. Most of you have probably heard about machine learning, but just in case there are some of you who are not too familiar with it, machine learning essentially is the scientific study of algorithms and models that allow a computer to perform a task without using without explicit instructions, right? So instead, usually what you just do is that you give the algorithm the data. So usually, if let's say we are talking about supervised learning, we give it a set of inputs and the corresponding outputs, and what you get are and what the algorithm would do is to learn the relationship between the inputs and outputs, okay? And today machine learning is everywhere, right? So I'm sure you have heard a lot of this in the news, okay? So things like self-driving cars, okay? So this is a necessary thing that powers the self-driving car is basically a machine learning model that recognizes the environment the car is in. Even simple things like if you go to your Netflix channel and there's recommendations for what you should watch next, those are also machine learning models. Weather forecasting, also machine learning. And of course, there's all those very well publicized competitions between AlphaGo and the best player in the world, who happens to be Korean, in the game of Go. And AlphaGo, of course, has now been able to defeat even the best player in the world, okay? All right. And so the machine learning model that we are particularly interested in is, especially in terms of material science, is the model which is the model what is known as AlphaFold, right? So for those of you who have been living under a rock, okay, AlphaFold is of course this very big achievement by DeepMind, where it is a machine learning model that was developed to predict the 3D structure of proteins, right? So a lot of the properties of proteins depend on its structure, okay? So basically the way that the protein folds. And this is actually similar to what we have in material science, right? So when we talk about material properties, we always think of it as a relationship with the structure of the materials and the composition of the material, okay? So in fact, AlphaFold was such a big achievement that the developers of AlphaFold actually won the Breakthrough Prize just recently in 2022, okay? So the equivalent problem in material science is, of course, let's say you are interested in developing, in trying to look for new materials for a particular problem, right? So let's say you want a new solar material or you want a new lithium-ion battery cathode material. You will usually go to some database and try to find out, okay, these are all the lithium-ion battery materials that are already known. How do I modify them to come up with new compositions? Or you can also use some form of structure prediction algorithm to come up with some new candidate structure or composition, okay? So you start with some candidate, and you need to do two things, right? So this is something that all of us in the computational material science fields know, all right? So the first step is to first relax your crystal and try to find some low energy or equilibrium crystal structure, okay? So in other words, we want to find the combination of lattice parameters and atomic positions that minimizes the energy of the structure, okay? At least the local minimum, all right? And given that equilibrium crystal structure, the next step that we do is, of course, we want to calculate the properties, right? And the properties, of course, it all depends on what kind of properties you're interested in, whether it is some energetic property like the voltage of a battery, or is it some electronic structure property like the band gap of a material, right? Now, and of course, over the past few decades, the way that we do this is basically through DFT relaxations and DFT calculations of the properties, right? Now, what I'm going to talk about today is how can we actually use machine learning to accelerate both steps of the process, right? And interestingly, we actually managed to figure out how to do the second step first. In other words, we, those of us in the community have done a lot of work in terms of being able to use machine learning models to predict the properties of a material from the structure, and we take the structure as a given input, right? I'm going to first talk about this, but in my second half of my talk, I'm actually going to talk about this very, very critical step. In other words, how do you actually get the equilibrium structure in the first place if you do not have that DFT relaxed structure, okay? So the type of machine learning model that my group works with, what I call materials graph network, or MagNet, okay? So this is a graph-based machine learning model, and it turns out that graphs are a very natural representation for materials, right? So you can think of the atoms as the nodes in the graph and the bonds between the atoms as essentially the edges in the graph. And you can represent each atomic species with a vector of numbers and each bond with a vector of numbers, right? Now, one of the unique features about our MagNet models is we actually also have this global state variable, okay? So you may have seen other graph representation for graph deep learning models for materials out there, but most of them would lack this global state variable. And it turns out that this global state variable is actually a very powerful concept that allows us to do very, very interesting with this model that you would not otherwise be able to do if you do not have it, right? And the global state variables, you can of course use it to represent some overall property of the material. Okay, so for example, maybe an external state like temperature or pressure or the entropy, or it can also be some abstract state like what kind of calculations was performed on this material. Okay, all right. Now, all the graph neural network models work roughly the same way. Okay, so MagNet is the same. The way that the graph neural network models work is basically you have essentially information flow or message passing between the components of the graph, right? So in our MagNet models, there's actually a three-step process. Okay, you start the first step, you actually update every single bond with information from the atoms that are forming the bond as well as the global state. Okay, and the next step, you actually update every single atom with all the bonds that are connected to the atoms and the global state. And finally, in the third step, you actually update the state, the global state with all the information from all the atoms and the bonds. Okay, and because we don't actually really know what the relationship, the functional relationship for these updates should be, basically we represent all these functions are modeled using neural networks because the neural networks are universal approximators. Okay, so and this is why this is also called a graph neural network, right? Now, given this architecture, you can actually then train machine learning models or graph deep learning models based on to predict any property that you are interested in. Okay, as long as you have sufficient data. And basically, the first thing that we did was to basically take the data that we already have from the materials project, and we start to fit train MagNet models to predict key properties of the materials, such as the formation energies, the band gaps, the bulk and shear modulus, and also do some classifications tasks like whether a material is likely to be a metal or an insulator, right? Now, it turns out that magnet models or graph deep learning models in general are extremely effective at predicting properties. So for instance, we can predict the formation energy of any crystals to within 28 MeV per atom. Okay, this is actually very good. I will show you why, okay, later. And I would say that this number is state of the art. Almost most of the graph neural networks models get something close to that. So for example, CGCNN also gets about 40 MeV per atom. SchuNet gets about 35 MeV per atom. And of course, this data is several years old, right? So when we made this magnet model, that was in 2019, and today is 2023. So it has significantly improved since then, right? And you can also predict things like the band gap to within about 0.33 eV, Bout and shear modulus as well. I'm not going to go into those details, but I want to show you why this prediction is so useful, right? So is 28 MeV per atom accuracy good enough for you to do materials design, right? And it turns out that it is, right? So this is actually a statistical analysis that was done by Professor Wenhao Sun back in 2016, where he basically took all the crystal structures in the inorganic crystal structure database, and he plotted the energy above ground state versus the total number of compounds in the ICSD, right? And what he found was basically about 80 to 90% of those compounds actually fall within about 100 MeV per atom of the ground state, right? So in other words, most of the crystal structures that people have made, so in other words, they are synthesizable, they are about within 100 MeV per atom from the ground state structure, right? And 28 MeV per atom is of course well within that 100 MeV per atom. And with this kind of accuracy, we are already able to predict with some degree of confidence whether something is likely to be stable or not, okay? Right. Now, one of the other things that I want to point out is, as I mentioned before, the amount of data that we have is very different across different properties, right? So, for example, we have energies for all the crystal structures that in the materials project database, right? So that back in 2019 or 2018 actually, that was about 60,000, but for the accurate bandgap data, we actually have only half of that, right? And this data quantity is actually a significant issue when we are using things like graph neural networks, okay? So one of the things that we as material scientists know is that there's a fundamental trade-off between the amount and the quality of the data that we have, right? So very high value data like experimental band gaps or accurate calculations of band gaps such as HSC calculations, they tend to be much more scarce than lower quality data like PBE band gaps, right? So for example, this is basically a statistics that we found that in terms of PBE band gaps, we can get to close to about 50,000 band gaps today just from the materials project itself, okay? And this is the most inaccurate band gap in terms of computations, okay? It is also least valuable, right? And however, you can also do band gap calculations using a HSC functional. Those are much more accurate, but your data size is much smaller, right? You only have about 6,000 of those. And of course, experimental band gaps are even less, right? And so what we wanted to do was to adapt our magnet models to deal with this data quality quantity trade-off in a way that doesn't require us to do more expensive calculations or do more expensive experiments to get more data, right? And it turns out that that global state that I talked about just now is an extremely powerful way to handle this problem, right? So the kind of model that we came up with is what is called multi-fidelity magnet models, okay? So what we do is that we label each of the data with the corresponding fidelity information. So for example, if it is PBE, we assign a value of 0. If it is HSE, we assign a value of 2. If it is experimental, we assign a value of 3. And we embed that data fidelity information into that global state vector, okay? So that fidelity embedding is actually learned by the model itself. Now, Other than that, the rest of the magnet models actually remain exactly the same as before, okay? And the difference between this and other kinds of transfer learning type models is that we no longer do a two-step training, okay? It's not that we fit one model and then we port the model over and try to retrain the model. Rather, what we are able to do now is that we can take all the data, the very, very large PBE data, together with the smaller HSE data and experimental data, and just build one single model that can predict the bandgap, the bandgap for any fidelity for any material. Okay, so does multi-fidelity magnet work? Okay, so the way that I show this is, first of all, we fitted single fidelity magnet models with each of the data sets. Okay, so you can see that your PBE data set, you actually get the lowest mean absolute error. So you are very accurate about something that you are very precise about something that's very inaccurate. Okay, so the mean absolute error is about 0.3 EV or so, but you will notice that the mean absolute error for things like the HSE bandgap and the experimental bandgaps are actually much higher, right? And the reason is, of course, the data sets for those, the size of the data set for those data is much smaller, and that results in a higher error in your machine learning model. Now, what happens if we actually combine the higher fidelity data with our very large PBE data? And it turns out that we can actually get something for free. We actually get a 40 to 50% improvement on our predictions of the high value HSE bandgap and experimental bandgap, right? So right after we actually combine either 2 fidelities or 4 fidelities to in a single model, we can actually get a 40 to 50% reduction in the mean absolute error. And in fact, the mean absolute error of the HSE and the experimental bandgaps are now quite comparable to that of the PBE bandgap data, right? So in other words, we are improving the performance on our high fidelity and high value data sets without actually having to make to actually calculate or measure more data, right? And so essentially we're getting something free, right? And we actually wanted to understand, why does this work, right? And it turns out that if you plot the TSNE plot of the latent structural features with and without the PBE data, you actually can see the reason why incorporating the PBE data, even though it is inaccurate, is actually so valuable, right? Without the PBE data, you actually do not get a very good separation of the latent structural features. You can see that all the high bandgap materials, which are the lighter points, are mixed in with the low bandgap materials, which are the darker points, right? While if you actually combine the PBE data, you actually have a good separation of the high bandgap and low bandgap materials, right? And it is this improvement in the underlying latent structural features that we believe is responsible for the improvement in performance in the HSE and experimental bandgap predictions, okay? All right. Now, I have talked about property prediction, and as I mentioned, historically, that has been the problem that most people in the machine learning for material science field actually focuses on, right? And but what about that first step, which is how do we actually get the structure in the first place, right? So previously, we are assuming that we already have the DFT relaxed structure, and then we just need to predict the properties. Now, if you have to do DFT to basically get the structure in the first place, you are really not saving a lot of effort. It's just about as expensive to run a DFT relaxation that as it is to just compute the energy, right? In fact, it's actually more higher computational cost to do the DFT relaxation. So this critical step actually needs to be accelerated. And so in the past few years, my group has been focusing very extensively on how do we use machine learning techniques to accelerate this portion of the materials design process, right? Now, one of the most naive ways you can do this, and is still actually surprisingly effective, is to just use your energy models, right? So as I mentioned, we already can fit a magnet formation energy model that can predict the formation energy to within about 28 MeV per atom, right? And with this, we can actually just naively try to apply the variational principle with the formation energy model, right? So when we do DFT relaxation, we basically change the lattice parameters until we actually get and look at whether the new lattice or new atomic positions is lower in energy than the previous atomic positions, right? And so we can do the same, and instead of just doing a DFT energy calculation, we can use magnet to actually predict the energy, right? And this was basically what we did. We actually used a Bayesian optimization with symmetry relaxation process. In other words, we constrain the lattice parameters and atomic positions by symmetry. We then use Bayesian optimizations to propose the next set of lattice parameters, and we then use the magnet formation energy model to basically predict the energy. And if it is a lower energy structure, we will accept it, and if it is a higher energy structure, we would reject it. And in the process, we basically can relax our crystal structure. Okay. Now we actually tried to use this approach in a materials design problem. We were trying to look for ultra incompressible hard materials. The way that we did this was to basically take about 5,000 structural prototypes. We do a combinatorial elemental substitution. So we substitute things like moly, tungsten, osmium, and rhenium, as well as boron and carbon into the 5,000 structural prototypes. And we generated about 400,000 unrelaxed crystal candidates, right? So 400,000, as you know, is not something you want to do with DFT, right? So you can't run DFT calculations of 400,000 structures in any reasonable amount of time, right? So remember, the materials project structure database is only about 140,000 structures, right? So you are doing 4 times the materials project to basically calculate 400,000 crystal structures. But with our magnet formation energy model and the Bayesian optimization algorithm, we can actually relax all 400,000 crystal structures. And we can do this in the space of a few hours, right? And after that, with the relaxed crystal structure, we can then use our magnet formation energy, bulk modulus, and shear modulus models to actually predict these properties. And using these machine learning predictor properties, we can already screen out the majority of our 400,000 crystal structures, right? So out of the 400,000 crystal structures, only about 1,600 of them have an energy above Hall of less than 100 MeV per atom, and a bulk modulus of greater than 250 gigapascal, and a shear modulus of greater than 100 gigapascal, okay? And from those 1,600, now we can actually do DFT calculations, right? 1,000 structures is quite doable. We went ahead and do our DFT calculations and validation. And eventually, after the DFT step, we only have about 140 crystal structures, and of which my colleague at UCSD, Professor Tian Luo, went ahead to synthesize this in his lab, and he actually managed to make all 8 of these identified candidates from our screening, right? So these are just 2 of the examples of the materials that were obtained experimentally. Okay, so there's this rhenium tungsten boride and this moly tungsten carbide structures. Okay, you can see that the experimental XRD pattern and the calculated XRD patterns are actually in very good agreement with each other. And he also measured things like the bulk modulus and the hardness using pulse echo measurements, and you can see that the experimentally measured properties are very much in line with what is predicted from our machine learning model as well as from our DFT calculations. Okay, so even something simple like this, you already can get a fairly, you can use it for effective screening of materials for various applications. Okay. Now, the other way that you can get an equilibrium crystal structure is to develop an interatomic potential. All right. So an interatomic potential is basically something that parameterizes the energy and forces on each atom as a function of the atomic positions, right? And in recent years, machine learning has been applied to develop interatomic potentials, okay? So this is one of the great success stories of machine learning in material science, right? We are now able to build interatomic potentials that are within sub-MeV accuracy of DFT calculations, all right? So This is actually a benchmark work that my group did in collaboration with a lot of the developers of the various types of machine learning interactive potentials. So things like the gap potential, the moment tensor potential, neural network potential, and the spectral neighbor analysis potential. I would just summarize by saying that basically the energies and force errors that you can get with all these formalisms are much, much lower than what you would be able to get with things like EAM, the traditional embedded atom method, and modified embedded atom method potentials. Okay. Now, so there are many flavors of all these machine learning interactive potentials. I'm not going to go through them in this talk. So one of the things that is limiting, however, in terms of machine learning interactive potentials is that the number of terms for all these formalisms grow combinatorially with the number of elements. In other words, you can actually build machine learning interactive potentials for fairly complex chemistries. You can go up to 3, 4, or 5, even 5 or 6 elements, all right? But as you go to increase the number of elements in your system, the number of terms grow combinatorially, and by the time you get to about 7 elements or so, it becomes very unmanageable. Okay, so it's very difficult to generate enough data to train a 7-element machine learning interactive potential. Okay, the other problem is that, of course, you actually always have to custom fit the machine learning interactive potential to each system and chemistry of interest, and you cannot use it for broad-based materials discovery, right? So when we talk about materials design, materials discovery, usually we are interested in almost the entire periodic table or a very significant sub-portion of the periodic table, right? So we need something that can work across most of the periodic table. So even back in 2019, when we first developed our magnet models, we already had this idea that perhaps it might be possible to use the graph neural network to build an interactive potential, right? And the reason why we thought of that is because the graph neural network actually lends itself naturally to a complex chemistry, because each atom has its own vector representing the chemical environment, right? Chemical character, right? So this is actually what was our initial attempt at building an interactive potential using our magnet model, right? So what you see here is this is an equation of state for one of the cubic crystals. And you see that we actually have very significant problems, right? Even though, yes, it seems that potentially this might work, but there are some artifacts in our predictions, right? So there's this discontinuity in the energy when it gets to the cutoff radius, right? So so our initial attempts were definitely not that successful. So first of all, we definitely need some form of smooth cutoff function to basically get rid of this discontinuity. And we also found that graph representations are actually not very efficient for interactive potentials, right? Because fundamentally, the graph message passing is still a pairwise interaction term, right? So of course, with more layers, you can actually get something close to like multi-body interaction terms, but that message passing is not a very efficient way of representing multi-body interactions, right? And in most systems, multi-body interactions are actually critical in getting a good interactive potential. So what we did was that we took some inspiration from the traditional interactive potentials, like the Tersov potentials, where essentially you have, you modify, you augment the materials graph with some form of n-body interaction, okay? So this is basically what we did. We basically, instead of just doing our message passing, we implement a scheme where we consider every set of 3 atoms, okay? And we then expand that interaction in terms of spherical harmonics, and what we get is that is this new architecture which we call M3GNet. Basically, all that we did is to basically invert this E to become a 3. Okay, it stands for basically materials graph with 3 body interactions. Okay, now so this is the architecture. What we then need is, of course, the training data to actually fit an interrupted potential using this new architecture, right? Now, the first thing that we did was to first try it out on some very simple data sets. Okay, so this is basically the set of individual data sets on nickel, FCC nickel and copper, and BCC lithium and moly, as well as diamonds, silicon, and germanium that we actually that we actually generated for our initial benchmark work on machine learning interrupted potentials, right? And what you will notice immediately is that the M3GNet architecture actually performs very comparably with the machine learning interrupted potentials, right? The errors are similarly low, especially compared to things like EM and MEM, right? And the false errors are also similarly low. Now, one advantage of the M3GNet model, however, is that unlike the other models where we actually have to fit each element in by itself, we can actually do what is called an M3GNet OR. In other words, we just take all the data and just fit one single model to the entire data set. And you will notice that basically the errors do not change, right? So in other words, this M3GNet model architecture has the advantage of being extremely flexible in terms of chemical complexity, okay? Now, to train what we call an AlphaFold for material science, what we did was to basically go back to our favorite database, which is the Materials project. There's actually this data set that most of you may not be even aware of, which is that the Materials project has done about 100,000 DFT structural relaxations since 2012, okay? So in its database, you have about 100,000 energies, about 10 million forces, and about 1 million stresses, right? And this is a very big and rich data set that we can just throw the entire data set into our M3GNet model. And in the process of doing so, what we hope to do was to basically fit an interrupted potential that can work for 89 elements of the periodic table, okay? So this is basically the result. These are some performance benchmarks. So in terms of energies, we can get to a mean absolute error about 33 MeV per atom. Very low, right? This is actually quite a nice error, okay? So of course, it's not as low as a custom fitted interrupted potential. Those you can get down to about less than 5 MeV per atom. But for a general purpose interrupted potential that works across the entire periodic table, this is actually a very good value, right? In terms of forces, we can get down to 0.07 eV per angstrom. We do slightly worse on stresses. The mean absolute error is about 0.419 gigapascal. Okay. With a universal potential, we can now begin to replace that step that we were struggling with, right? So we can now do structural relaxations, right? So using a test set of about 3,000 structures, we actually did structural relaxations on them and compare them with the DFT relaxed structures. And what we found essentially is that we can get volumes which are about within just a few percent of what you actually get with DFT, okay? So in other words, in terms of relaxing the crystal structure, we are doing extremely well, right? In terms of energies, as I mentioned, we can actually get energies within most of the structures. We actually get energies within the ground state of about 30 to 40 MeV per atom. So very, very good, right? And with that, we can actually get do stability predictions, right? So we can take the M3GNet predicted energies and do a phase diagram and then calculate the E above Hall. And what we found was that the M3GNet predicted E above Halls and the DFT predicted E above Halls are actually fairly consistent with one another, okay? Now, of course, interrupted potential is not just used to relax tracer structures and calculate the energy, right? You can essentially use that to calculate any dynamic properties, right? So you can even calculate things like the phonon DOS center, okay? You calculate the phonon dispersion, and you look at the center of the phonon DOS, density of states. And what we found was that essentially we can actually get the center of the phonon density of states to a fairly good accuracy. We can simulate things like the bulk modulus, okay, just from finite displacements. And we also can get the bulk modulus to very good accuracy. We can even run molecular dynamic simulations for and get the diffusivity, right? So this is an example of a lithium superion conductor, Li3YCl6, and the yellow line is basically what you get with ab initio molecular dynamics, and the blue line is basically what you get with our M3GNet model. And what you see is that you can actually get a fairly consistent result between the two, right? Now, this is actually data that is not in the paper that was published, okay? So we actually subsequently continue to explore what are the limits of this M3GNet potential, and it's very interesting because we are actually surprised ourselves at how well it actually works across a lot of systems. So we took about 6,000 cubic crystals from the materials project. The reason why we choose cubic crystals is because there's only one lattice parameter to worry about, and we just calculate the M3GNet lattice parameters and look at the percentage error, and you see that essentially almost all the cubic crystals fall within 1% of the DFT cubic lattice parameter. Okay, you can also calculate the what is called the delta gauge. So this is something that was come up with by the Jahe, who actually look at the differences between, say, a pseudopotential code and an all-electron DFT, and he was essentially looking at the errors in the equation of state, okay? And when you look at that, the pseudopotential codes usually get within about 0.5 to 1 MeV per atom of the all-electron DFT equation of state, right? And what you notice is that M3GNet is actually achieving something that's almost the same error relative to a pseudopotential DFT code, okay? So in other words, the accuracy is actually extremely good, all right? All right, now with M3GNet, we now have the ability to do completely just machine learning based structure prediction and property prediction, right? So what we did was to come up with this database called Metaverse.ai. It is not meant to substitute the materials project. It is meant to be a complement to the materials project. And this database is meant to be just a pure machine learning database. Our target is to go 1 billion materials and beyond, okay? And this database would have machine learning property predictions, things like the structure, the band gap, the phonon dots, and so on and so forth, right? And the predicted structures from these machine learning models would also fit into the materials project. If we predict something that is likely to be stable and have good properties, the materials project will do DFT calculations on them. And once the materials project actually get new structural relaxations and training data, we can then feed back to the model development for M3GNet, and hopefully we can build better machine learning models for material properties, okay? All right, so this is what you get if you go to Metaverse.ai today. You can do any kind of searches. You can look at the crystal structures. And other than the relaxed crystal structure, you can actually get the formation energy, the band gap, the bulk and shear modulus predictions. I would note that uniquely among databases, okay, so most of the database out there, you see there's the predicted DFT band gap, right? We actually predict the experimental band gap. So in other words, using our multi-fidelity magnet models, we can actually give you a prediction for the experimental band gap of a material, okay? And we actually have predictions for all 140,000 of the materials project materials, okay? The reason for this is not because we require them, because you already have DFT calculations done on them, but rather this is just for you to look as a benchmark, just to compare the values, okay? We have about 31 million novel materials that's been generated, and of course, like I mentioned, you have different types of different fidelities of band gap available, right? So I just want to show you some, in the last few minutes, I'm going to show you some initial results that we have used this model to actually design lithium-ion battery materials. So one of the major areas of interest in lithium-ion battery research right now is to develop all solid-state batteries. And one of the key components to all solid-state batteries is the lithium solid electrolyte, okay? And this solid electrolyte, there are a complex number of set of properties that you have to satisfy. You want something that is stable. You want something that's electrochemically stable as well. And of course, you need something that conducts lithium very quickly, right? And what you notice is that all these properties are based on you can actually predict them from computations, right? So you can do a DFT calculations of the energies. You can run NEB calculations on the activation barriers. You can run MD to get the mean square displacements of ions and predict the ionic conductivity. You can also get the band gap and power and shear modulus, right? Now, what we want to do is, of course, instead of doing DFT, we want to do all this with just our M3GNet models, right? And it turns out that M3GNet is actually extremely useful, right? So I already talked about ionic conductivity. You can actually get really reasonable predictions of the ionic conductivity, at least good enough for you to exclude bad conductors from M3GNet. But even for something like the electrochemical window, you can already see that with M3GNet, you can get a good prediction of the electrochemical window that is comparable to basically what you get with DFT, right? And so, in other words, we don't actually need DFT, at least at the initial stages of screening, okay? So, right now, we are at 31 million structures. About 1.8 million of those structures have an E-Hall of 0 or less than 0, okay? And we are now doing this massive scale for lithium superionic conductors. And as you can see, this is basically a screening protocol that we actually use in our group based on AIMD simulation. We basically get the mean square displacement at 1200K and the mean square displacement at 800K. And basically, you'll notice that all the known lithium superionic conductors actually fall within this regime. So materials sitting there have very high ionic conductivity, very high diffusivity at the lower temperature, and the activation barrier is also sufficiently low, such that we would have some confidence that it might be a good conductor at room temperature. Okay, and what you notice is that there are a lot of points that are sitting here that no one has actually explored experimentally for lithium superionic conductors. Okay, all right. Now, I'd like to conclude with this. So I'm sure, hopefully, I've convinced you that this is a very exciting development. I myself am very excited. In line with all the things that my group likes to do, we always like to make our source code open source. Okay, so today, if you want to try M3GNet out yourself, it's actually available on GitHub in our group's repo, M3GNet. This is the original M3GNet repository. It is implemented in TensorFlow. It is already fully functional, but there's no multi-GPU support, right? We are actually working with Intel right now to re-implement M3GNet in Deep Graph Library and PyTorch. Okay, this repository is called MatGL. We actually have completed the initial implementation for both the MagNet and the M3GNet models. There is multi-GPU support, but it is of course still being tested. There might be bugs, okay, so I don't want to promise you that it is fully functional, but if any of you want to try it out, and you can report any bugs to me, okay? And of course, because a lot of people in the community are actually extremely interested in M3GNet, people have started integrating them into various software, commercial or open source. PyMatGen, of course, has a ability to relax crystal structure using M3GNet now, okay, because I'm the developer of PyMatGen. The Amsterdam modeling suite actually also integrated M3GNet into their system. They actually even have a tutorial about how to use their software to run M3GNet relaxations. There is someone who actually developed a LAMPS interface to M3GNet as well, Advanced Soft from Japan. And just to conclude, graphs are very natural representation for materials, and in fact, with graphs, you can build universal machine learning models. Machine learning accelerated materials discovery has been demonstrated even without M3GNet. Okay, so I am very confident that machine learning would be a very powerful tool for us in exploring new materials for various applications. And hopefully I've convinced you that the M3GNet architecture is very robust. We are still working on new developments on it. Right now, I believe that a lot of the constraints are actually in terms of the DFT training data. So in other words, how accurate are just PBE calculations, right? Can we actually get more accurate calculations for that purpose, right? All right. I just want to acknowledge Chi Chen again because a lot of this was implemented by him. These are the three there's this paper, of course, is in Nature Computational Science, and if you want the archive version, there's also an archive version. The repositories are on GitHub. I encourage you to try them out. And of course, if you just want a layman read, there's also this press release from UCSD on the M3GNet development. Okay, and I'm happy to take any questions. Thank you.